So JESD204 purpose, history, and future. It started in 2006 when the speed of the converters began to rise, and there was a need for a serial access to these data converters. And at that time, the speed was 3.125 gigabits per second, which was, I think, pretty fast at the time. The standard 204 quickly got a revision called the A revision, when multiple lanes were introduced with link synchronization. Initially, it was a single lane talking to a converter device. Then the B standard increased the speed, still keeping the 8-bit and B encoding up to 12.5 gigs, and separated the clock domains between the RX and TX devices, and introduced something called deterministic latency, which we'll be talking about later in the presentation. Followed by a 204C standard, which is the current state of the art, where there were features introduced for data correction and error detection, so a FEC basically, and a CRC, as well as the speed increase to 32 gigs, and the change in the encoding scheme to 6466B, dictated by the speed increase. And now the 204D that we are working on in the standardization group is going to use a PAM4 PHY up to 116 gigs with an RS FEC, Reed-Solomon FEC, in place of the Firecode FEC that was in the C. So the speed is going to increase again, and then we're going to have probably different implementations for the FEC depending on the lane reach of the application. So ultra short reach to long reach, depending on what you're doing. Right, so now some differences between the two standards, or the versions of the standard. So in the 204, the A and the B, you had 8-bit and B encoding, where basically you would take 8 bits of data and encode it via lookup table into 10 bits of different polarity, plus or minus polarity encoding, just to keep the amounts of zeros and ones on the link sort of stable. And the 204C, we changed the encoding to 6466B because of the speed increase, where 64 bits of data is unaltered and only a 2-bit sync header is added onto the data. And in 204D, because it's based on an RS FEC works with, for this case, it will work with 10-bit symbols. So depending on the FEC type, if it's a 542, 512 FEC, we'll have 512 10-bit symbols, so a big data block. There will be a sync header appended to it, prepended, and a FEC word appended in the end, which allows to correct errors that appear on the link. And also the way the link is initialized varies between the different standards. In the 204A and B, and mostly you'll be working with B these days, is sort of like a handshake mechanism where the RX requests synchronization from the TX sends special control characters called K28.5 characters in the 8-bit and B encoding, which the RX synchronizes to, so it finds the word boundaries. And when it establishes a word boundary, it deasserts the sync, so it says, okay, I don't need you to send the sync anymore, and the TX will then send a initial lane alignment sequence, which is sort of like a hello sequence of incremental bits plus some configuration data that is only checked, and then that will be followed by actual data. And in the C and the D standards, the mechanism differs. The TX is sort of blind to the RX, it's unaware of what's going on in the RX, and it just transmits data. And the RX will sync to these sync headers. We'll find those sync headers in the data stream. It will perform framing lock to these bigger structures of framing inside of the standard and start outputting data without the TX having to do anything. And the same happens in the next, it will happen in the next revision, the D revision. Probably a similar scheme, except for maybe we'll be doing a require FEC decoding success just to make sure that FEC is in the proper position. What this means is that in the B standard, you would require a separate pin or some software control just to carry out this handshaking, right? So we have an extra pin. And some use cases and application examples. So where is JSD204 used? In telecommunications, a lot in wireless, 5G RF front ends, beamforming applications. In aerospace, for satellite communications like the Ka band, transmission, high gigahertz frequencies, and maybe some imaging applications. And the medical sector, I heard talks about people using it into scopes that go inside of people, so transmitting data from there, or some scanners, medical scanners. Basically, anywhere you have use for high-speed ADCs or DACs, that's where you can find JSD.